Okay, so here's our hand-waving version. Our delta z delta t is equal to the rate at which f changes with respect to x times the rate at which x changes with respect to t plus the rate at which f changes with respect to y times the rate at which y changes with respect to t. You say that yourself often enough, it'll start to make sense. So we rewrite that expression at the top of the page for reference. As delta t approaches 0, then provided the f, x, and y functions behave themselves decently. Now we'll have to define what decently behaved means. Basically this means that the functions are differentiable and defined and so forth. And of course if it's differentiable it's defined, but we'll worry about that later. We'll worry about the rigorous meaning of decently behaved. For right now we'll just say as long as these functions behave decently, which most of the functions we've talked about do, then the approximation becomes equality in the limit as t approaches 0. And the delta z over delta t becomes a dz dt. Now, we therefore can write the chain rule. Dz dt is equal to, well, of course, is equal to df dt. We could use either notation. The df dt, or the dz dt, then becomes equal to the expression that we had here. Partial of f with respect to x dx dt plus a partial with respect to y dy dt. This means that at any given value of t, we have a value of x and a value of y that combine to give us a value of f, and that value of f changes at that t instant at this rate. Now the next instant, a slightly different t, the rate will be a little bit different, typically, unless we have a function that's at least temporarily constant. So that's our chain rule. We're going to see in a minute how to apply it. It's pretty straightforward.